So, someone is making a claim that the type of pet a person owns is related to the individual's mindset, may it be an optimist, a pessimist, or a realist. And we look at three common types of pets, which would be cats, dogs, and ferrets. And we went and asked people, well, what is your outlook in life? They said optimist. And do you have a pet? And they said, oh yeah, yes, I have cats. And we collected that sample, and that many number of people gave responses. So if you add all of those together, you would know the number of individuals that we spoke to. And as always, the very first step is to define the null and the alternative. So the null is that the person's mindset is independent of the type of pet they own, and the alternative is just the opposite of the null, and it just says, well, the person's mindset is dependent on the type of pet. Alpha is 0.05. So if we have to reject the null, or if we rejected the null, the probability of error in rejecting a null under the given null has to be 5% or less. So 0.05 to 5% or less. If we go back to the chi-square goodness of fit test, what did we find prior to finding the test statistic? We needed to have the observed and expected frequency. So whatever we see here in this table would be the observed frequencies. We observed everything. So this would be the table of O's. Our objective is to find the expected frequency. In other words, what should we expect to see if things were independent? So we want to find the expected frequency for each of those values. So we want to know every single one of them how do we find that? So we multiply the row total and the column total for each cell. Now, where do we get this information from? This information comes from the observed data. So the row total would simply be the sum of all the values that you see along the rows. So 74 plus 16 plus 32 in the table of observed frequencies would give us 122. Likewise, if I add the second row of observed frequencies, I would have 40 and 121. And the last row, the observed frequencies, 72, 82, and 84. We do the same for the column total. It's 112, 182, 186. Do you see what I'm doing? I'm adding all of these values across the rows to get the column total, across columns to get the row total. And the last one, 81. And the expected frequency for a given cell is simply the product of the row total multiplied by column total divided by the grand total. What is the grand total? It's just all of these values added. So I have 243, 323, and 327. And if you add across here, you would get the same. If not, you made a mistake. So if you add all the column totals, it must match the sum of all the row totals. So for each cell, we pick the row total, multiply the column total, divide by the grand total. So for the very first cell, which is right here, the row total is 122, column total is 186, divided by the grand total 327. And what do we get?
$69.4 rounded.
69.4.
Rounded.
And what should we multiply here for the second sum?
Times 122 divided by 327.
16 multiplied by 122 divided by 327. I'll give you about 5 minutes, you can complete the table. Do we have the values? That's can verify too. So, what you guys get for that sum?
What? 22.4?
123.4
Just 22.4.
or 22. Okay. Got to try, people.
30.2. 30.2.
30.2.
68.8.
68.8.
22.2. 29.9. 47.8. 15.4. 20.8. It's
And
47.8 on the. You were 27.8, but it's actually 47.8 on the.
47.8. So what we have here is the table of ease. Yes.
If we round as we have been doing, then the 29.9 actually was 30, going 97.
We'll just leave it as is. It's fine. It's not going to make a huge difference. But if you want to, you can round it to 30, that's fine. So last time, with the goodness of fit test, when we had a bunch of O's and a bunch of E's, what did we do? You can look at the notes. When we had a bunch of O's, a bunch of E's, and we wanted to find the test statistic. How did we find that test statistic? Sum of all O minus E squared divided by E. It is the same thing like we did last time. So we have the O's, we have the E's, so we have to find O minus E squared divided by E. I showed you an easier way to do this using the calculator last time. Do we remember?
Put it in the list of the calculator.
Put everything in the calculator. Put all the O values in list 1, E values in list 2, and simply do L1 minus L2 squared divided by L2. So I have all the O values in list 1, E values in list 2, the observed frequencies and the expected frequencies. But one thing that you've got to keep in mind, if you go row by row with this table, you have to enter things row by row over there. So this cell here has to match with that cell over there. In other words, you can't enter list 1 as 74, 32, 16 and then go over to the expected frequencies and enter stuff as 69.4, 68.8, 47.8. The order is important, so they go hand in hand. So you've got to match the observed and the expected frequencies. So we find L1 minus L2 squared divided by L2, save it to the third list, L3, and that's all we get. And one last dance of the information in list 3, which gives us 42.427 as the sum. So don't pick the average, it has to be the sum. So it's 42.427. And of course, if we have to use the critical value method, you need to know the distribution of the test statistic. Last time the distribution was chi-squared with degrees of freedom k minus 1. This time, the distribution is chi-squared. But it is R minus 1 multiplied by C minus 1. What is R? R is the number of rows. C is the number of columns, so we have 3 and 3. 3 minus 1 times 3 minus 1, 2 times 2, we get 4. So we know the distribution, we know the degrees of freedom, now we have to find the critical value. How do we find the critical value? It is chi-squared So I'm looking at the area below. What did we use last time to find the critical value? We needed something. Okay. So we have the degrees of freedom. Of course, the table there uses the area above. My notation, I'm using the area below, but do pay attention to what type of table you have. In our problem, where is the area? The area is on the right cell. And what is that amount? That is equal to 0.05. So we go to column 0.05, and we have to come down to row 4, because that is the degrees of freedom. So 2 times 2 is what we had, and the critical value is 9.488. Does that make sense? Yes? So we found the critical value to be 9.488, and what is our test statistic? The test statistic is 42.427. So 0 is right over here. That point is 9.488, and where should 42.427 be? Did the test statistic fall in the rejection region? Yes. Should we reject the norm? Do you believe that the person's mindset is dependent on the type of pet they own? Did we find evidence toward that? We rejected the norm. Yes. We found significant evidence toward that statement, but that doesn't imply one resulted in the other. In other words, this is not a cause and effect relationship or conclusion. All we are saying is, based on the data that we have, we found significant evidence to indicate that a person's mindset is dependent on the type of pet they have. Does that make sense? How do we find the p-value? How did we find the p-value last time? The chi-square test is always right-tailed. So the p-value here is the area above the test statistic. In other words, we want to find the area under the curve above that point, and the curve kind of goes towards 0. So even before you start the problem, you should have an idea as to what that value would be. Am I going to expect a value close to 1 or something really, really tiny close to 0?
Very small.
Very small, close to 0. We start at the test statistic, 42.427. We end at E99. And what goes next? The degrees of freedom, 4. And what do we get?
(1.34 e to the 8), negative 8, sorry.
That is a very small value. In other words, it's going to be close to 0. So based on the evidence that we have, based on the sample that we have, if I rejected the null and I concluded that there is dependence, that they are related to the person's mindset and the type of pet they have, the chances of me going wrong is about 1.34 times 10 raised to the negative 8. And it's a very small probability, in the sense, by all means, that we can comfortably reject the null and conclude that we found some evidence to support the alternative. Does that make sense? Good. Okay. So there is no way to escape finding the expected frequencies. But once you have the observed and expected frequencies, we could actually use the calculator to get the test conclusion. So how do we go about doing this? Press second, X in this, that button, second followed by that, and you should see a bunch of letters. So those are names of matrices. Oh, you may say, well, what is a matrix? A matrix is just a table. Easier way to look at it. So what we want to do is we want to edit the matrices. So I'm going to go to the first one, and I want to specify the number of rows and the number of columns that we had in our problem. So matrix A would be the observed frequencies, matrix B would be the expected frequencies, and we're going to fill them in. So in order to do that, I've got to let the calculator know the dimension of the matrix. So it is 3 by 3. There are 3 rows and 3 columns. So I end up getting a matrix. Good. Now we have to start entering stuff. So what are the expected frequencies? That erase them. Oh, excuse me, observed frequencies.
$74.
74.
32. 16. 81. 16. 24. 31. 12, and 41.
41. Oh, we're good. So I've entered the table of observed frequencies and I've saved that to matrix A. Second mode to exit. And we need to put in the expected frequency, so I'm going to repeat the process. Second, X index. Switch over to edit. And this time we have to define the second matrix, B, to have the expected frequencies. Again, how many rows and how many columns do we have? We have 3 rows, 3 columns. And we just have to enter all the expected frequencies, and what do we have? 69.4, 22.4, 30.2. That's a 9. The last one's 20.8. Okay, so we took all the observed frequencies, we put it in matrix A, we took all the expected frequencies and we put it in matrix B. Press start. Go over to tests. So there are 2 options. C, it tells us chi-squared test. D is chi-squared GOF test. Now that is what we did last time, the goodness of fit test. This time, it is a chi-squared test, so we've got to select that. By default, as you can see, it saves the observed, or it recognizes the observed frequencies to be in matrix A, expected frequencies to be in matrix B. Isn't that what we had? Right? Pretty easy. So the only tough part here is to find the expected frequencies. Once you find that, it's easy. Are we clear? Yes. So a test for homogeneity is no different from a test for independence. In terms of interpretation, they differ, and that's all. What do I mean by that in terms of interpretation? Well, in my example, I said, oh, the mindset of the person and the type of pen. But suppose if you want to say, if there are no changes whatsoever across the spectrum of treatments, then we say that they're all homogeneous. What do I mean by that? Let's say you have some sort of a condition some sort of immune response. And here we have a controlled drug that is currently in the market. So we have one available. And the proposed treatment. And lastly, placebo. We will do an example on this next one. So we want to measure the immune response in 2 levels, great, poor, and control is the current drug that's in the market, treatment, something that we came up with, and then naturally the placebo. What does homogeneous mean?
Alike. Like the same, like.
They're all the same. Now, in a practical sense, if a new drug, is actually great, what should you expect to see? Let me just say this. 30 individuals showed great immune response with the control drug. 12 showed poor immune response with the control drug. What about the treatment? What should you expect if the treatment is actually a great treatment? What are the number that we have here? Should it be bigger or smaller than 30? Bigger, right? Maybe about 50. What should we expect there? Smaller, maybe, 6. What about this, placebo? Should it be bigger or smaller? Smaller, right? How about that? I mean, it's just a placebo. Maybe it doesn't even work, right? Good, poor, whatever. I'll just call it. Would you consider that these values across the levels are homogeneous? No. So that is why we call this, if you have a problem like this would be a test for. Right. But in a sense, a chi-square test for independence and this are pretty much one and the same. Do you agree? What we did earlier today and the example that I gave you now, they're pretty much the same. But it comes down to what you're applying to. Next time I'll do an example. Perhaps I'll do one in psychology where you have 3 different therapeutic techniques and you want to see what kind of behavioral changes the person had. And if all 3 techniques are the same, then they're homogeneous, right? And I can't say that one treatment is better than the other. But if one technique is definitely better, then I shouldn't be seeing a homogeneous case. Does that make sense? Okay, are we clear? So one more example. Next time, we're going to do the same test, but we'll write the null, the alternative, step 2. We'll find the expected frequencies, but we'll do the rest using the calculator. Does that make sense? Yes. Okay. Good place to stop.